Hello and welcome to another video. This is a very interesting question I was shown today. It totally caught me out as well. It's when Weierstrass substitutions go bad, and turn into improper integrals even though it's not obvious. Now I'm not going to do the first two parts of the question because they're pretty straightforward. I'm going to talk about the last bit, which is an integral. And it's an integral where it's not obvious that it's an improper integral, because normally improper integrals are obvious. Maybe we get an infinity at the top, or an infinity at the bottom, a negative infinity at the bottom, or maybe we get something a little bit more subtle like this, 1 over 2x minus 3, x plus 1, and you also have to spot that there's a discontinuity in the graph at 1.5, and therefore you need to handle the limits by breaking it into two parts. So you need to handle an integral by breaking it into two parts and treating the limits carefully. So those are the typical improper integrals. What, as far as I'm concerned, isn't mentioned in the textbook, but certainly appears in this paper, and they do that in further maths. Watch out for it. Hopefully this comes up now and you can not be caught out by it. But what they don't mention is if you've got something like this, which I've already written down, so I'll go over here. This is what we're integrating, this function, Now, we already know that this function is the same as this, and I haven't bothered changing the variable yet. I'm still with respect to x, I've still got the same limits. Now, what you have to recognise is that t is tan of x over 2, and so when x gets to pi, which is definitely between 2 pi over 3 and 4 pi over 3, this takes a value of infinity. Now, what sense does it make here to have 2 infinity squared plus 2 divided by what's eventually going to become 16 infinity squared plus 16, plus 8 times infinity plus blah. It doesn't make any sense when you put that in there, so you have to handle it with care. It's an improper integral, and that's the key fact. Now, the best way to do this, so look out for that. The key point of this video, if you understand nothing else, is if you've got a Weierstrass substitution and it goes across pi, you're in trouble. You have to break it up into two parts. It's an improper integral. That's the key thing. I did actually check that my thinking was right, and I found this interesting article on the Maths Stack Exchange where somebody's got a very similar looking question. It's not the same question, but they're just asking like the question. You can see the thinking's gone exactly as mine did today, really badly in class. Like I was like, looking at this, I was certain I was right, so I actually checked it on the calculator and realised, no, I'm definitely wrong. They need the plus pi. But yeah, this poster has thought the same thing, completely missed it. They've argued the same way, like this hasn't got a discontinuity, this hasn't got a discontinuity. When they draw the graph, no discontinuity, vertical asymptotes are shown, and people are saying, yeah, look, when you've got the Weierstrass substitution, you have to be really careful over pi because it's tan of x over 2, and so you get tan of pi over 2, which is infinity, in your integral. So you must break it up, basically. So let's see how to break it up. Well, seeing as pi is the problem here, because tan of pi over 2 is infinity, that's why we're going to break it up into the following: 2 pi over 3 and pi. And I'm going to still write down this as x as a function of t, if that's alright. I'll deal with the substitution in 1 second. 4t plus 1 all squared. So I haven't changed this for dt yet, plus, and then pi to 4 pi over 3. And then I'll write this out again, over 4t plus 1 all squared plus 5 dt dx. Okay, so that's broken it up. Now we're going to have to think carefully about what kind of infinity we get as well. And this is all about the tan graph. If I can just quickly draw a tan over here, it's going to help me. It looks something like this, Remember, it's negative infinity just after pi, So what are we doing here? Well, when we're converting, this is pretty easy. dt by dx is half sec squared dx, so 2 dt is 1 plus t squared dx. So I can swap the 1 plus t squared dx with another factor of 2, making this appear. 4 over 4t plus 1 squared plus 5 dt. Good, I've swapped that. Now let's think about the limits now. Tan of 2 pi over 3 divided by 2, sorry, x, these are the limits for x. So 2 pi over 3 divided by 2 is pi over 3. Tan of pi over 3 is root 3. Now, what about when we get to pi? Well, we've got tan of pi over 2, but notice we're approaching it from below, because we want to now actually treat this. Sorry, I've just lost connection. I should get my pen back in a second. Yeah, cool. we want to now treat this to consider very carefully whether we've got positive infinity or negative infinity here. And we're basically, you know, let's consider this, let's write it down in limit now. The limit, because this is what I really want, the limit as, I'm going to have to use a different letter to t as well. I'm going to say the limit as p tends to infinity of p here. Now the reason why it's going to be positive infinity, and that kind of is important, is because think of the tan graph, yeah? Like, this is pi over 2, sorry, I should write pi over 2 there on the tan graph. When you're just to the left of that, yeah, when you're underneath that, like, if you like, then we've got positive values of y, and therefore this is tending towards positive infinity, yeah? But later on, when we're going from pi up to 4 pi over 3, we're going to be doing tan of pi over 2 down there, but we're going to be slightly bigger than that, yeah? And therefore that needs to be tending to negative infinity, just because we're going from pi up to 4 pi over 3. So as you can see, we're just after the pi over 2 value now, and that's why that is negative infinity. I think that's probably the bit which will confuse people the most, yeah? And that's why I'm going to write this as plus the limit as p tends to minus infinity, yeah? And you can put minus infinity here if you like, of p and now tan of 4 pi over 3 divided by 2, that's tan of 2 pi over 3, which is minus root 3. This is the other reason it has to be kind of going from minus infinity, because it's the only way which makes sense, if you see what I mean. Is that clear enough as a pig? It's the only way it makes sense, because you want it to go from minus infinity up to minus root 3, so it's nice and clear that you're getting, you know, it's continuous, yeah? Okay, of 4 over 4t plus 1 squared t plus 5 dt, yeah? And that is the trickiest bit, realising that that's going to be negative infinity, yeah? Basically, and you might want to write it, maybe you want to write just negative infinity down there instead of p, but I like the limit in there, I really do. I like to write it with limits. I think they really do, they insist on writing it with limits. I don't know, I like writing it with limits anyway. Okay, so, okay, what does that give us? Well, you might get slightly stressed about integrating that. Don't get stressed about integrating that. It's a 1 over x squared plus a squared version, which is in the formula book, and goes to, if you integrate it, 1 over a arctan x over a. Yeah, so that's all I'm using here. Now, also, you might get stressed with 4t plus 1, but if you do a quick substitution, hopefully you'll realise that the 4 on the top is really useful with a 4t plus 1 squared on the bottom. You know, let's just do a quick side note that if you're doing 4 over 4x squared plus x plus 1 squared plus 5 dx, yeah, let's just do it with x's. Let u equal 4x plus 1. You're going to get du is 4 dx. In other words, the 4 dx is going to become a du, so it's going to be 1 over u squared plus 5 du. And can you see now why that ends up integrating to 1 over root 5 arctan of you know, u over root 5, yeah? And that's why we get what we do, which is 4t plus 1 over root 5. So, okay, we're now in a really good position. Yeah, we can finish the question now, and we can avoid missing the plus pi in the question, which is so easy to miss, it really is. Okay, so what does that give us? You should put it on your calculator, because your calculator will show you got it wrong. That's one thing I will say. So this is a limit as p tends to infinity, positive infinity that is, of, okay, right, so what do we have? 1 over root 5, 10 to the minus 1 of 4t plus 1 over root 5 between the correct limits of p and root 3, plus exactly the same, but for this one only just slightly different with that negative infinity and different limits. 1 over root 5, 10 to the minus 1 of 4t plus 1 over root 5. God, it takes a while, doesn't it, writing it down. And now we're going from p to minus root 3, and p represents negative infinity here. So plug it in carefully, yeah? What are we going to have? We're going to have, right, well, we're going to plug root 3 in first. We're going to get 1 over root 5, tan to the minus 1 of 4 root 3 plus 1 over root 5. Then we're going to get minus, now think of this, yeah? P is tending towards positive infinity, yeah? What is inverse tan of positive infinity, yeah? When you're approaching positive infinity from the left-hand side? Well, once again, we can use the fact that that equals pi over 2, yeah? Oh, which will be in, you know, let's take the 1 over root 5 out, yeah? And so that's going to give me, oh, hang on, I put the limits in the wrong way around. How silly of me. That should be the other way around. I apologise, everyone. Very, very silly of me. We're plugging p in first, and maybe you even want to write this down, of tan to the minus 1. But you're going to be doing infinity when you plug in that p in. It's infinity from below. It's growing towards infinity. And so that's going to be inverse tan of infinity, and that's why that is positive pi over 2. And then we're going to get minus, plug in the root 3, and we get arctan of root 3 plus 1 over root 5. And then for the next bit, we get exactly the same. It gets a bit boring writing down all the algebra in this, but you have to handle it carefully, don't rush it. Okay, right, we're plugging in minus root 3 first. Let's just plug the limits in the right way around. Dear oh dear. Inverse tan of minus 4 root 3 plus 1 over root 5 minus, now think about this time it's negative infinity. Now what is inverse tan of negative infinity? Well, think about the graph once again, yeah? Oh, let's go and see that tan graph. When you're at negative infinity, yeah, if you're in this range, remember arctan as well, it's only defined from minus pi over 2 to pi over 2, yeah? And so this one's going to give you your minus pi over 2, because you're down at negative infinity there, but within the range of the arctan graph. So that one's got to be inverse tan minus pi over 2, so we're going to have minus pi over 2, yeah? Another way of thinking about it is, you can do this, inverse tan of negative infinity, because tan's an odd function, then it's minus inverse tan of positive infinity, and so it's minus pi over 2. That's possibly a quicker way of getting there. So we're going to end up with pi over 2 plus pi over 2, which is where they get their extra pi from, and if you times top and bottom by root 5, I believe you get the answer which they've given, which is, sorry, I'm struggling to move this around. You now get that answer perfectly, basically. I'll just check, times top and bottom by root 5. So what am I going to have? I've got the pi, you can see that becomes a plus, and we've got the pi, let's just put that leading. And then we've got this one, which is positive, so let's actually times top and bottom by root 5, I get 1 minus root 5 minus 4 root 15 over 5. And then I'm going to get minus, so 10 to the minus 1, and then basically the other way around, positive 4 root 15 plus root 5 over 5. Is that what they've got at the end? I think it is. So root 5 minus 4 root 15, yeah, perfect, and then root 5 plus 4 root 15 back. There we go. Handle those limits with care. Damn, it's easy to make a sign error, or just an error with negative and positive infinity on that question. That is not an easy question, so watch out when Weierstrass substitutions go bad. Yeah, it is a very, very unobvious improper integral. Okay, hope you enjoyed the video, hope it was useful, and keep up the hard work. You're doing great. You are doing great.